Very good morning to all of you. As Scott mentioned, myself Abhisek Chatterjee, and I'll be giving a talk on upper ocean variability of the South Tropical Indian Ocean. Primarily I'll be talking about how the interbasin connections that drives this upper heat content variability in the South Indian Ocean, and how these connections are changing with respect to the climate change. So that will be the primary focus of this talk. The talk is contributed by my PhD student Sajid, who is also here, and my co-authors Raghu Muthugude, Michael McFadden Shenoy, and Vinay Chandran. So to begin my talk, this is a picture depicting the top 400-meter heat content trend. And what you see here is that the entire Indian Ocean is basically warming. So I'm sure that it is a very familiar picture for you. But there are a few things to note here. The first is the South Indian Ocean, or the regime of westerlies, are warming much faster than the rest of the basin. But there are other two regions. That is, one is the South Tropical Indian Ocean, which is between 20 to 30 south, and the and the thermocline ridge region. These are the two regions are also warming much faster than the rest of the basins. And the North Indian Ocean is comparatively less warming than the South Indian Ocean. So there is an asymmetry in the hemisphere. And this asymmetry is not new to the Indian Ocean. It is there for the global basin as well. So this picture is taken from Saurav, who is also here. So it's showing the time series of heat content, time series of temperature, I'm sure. Heat content anomaly for the northern hemisphere, which is on the left, and the southern hemisphere in the right. And what you see here, there is a switch in the sign for the southern hemisphere. So after 2010, there is a hemispheric asymmetry which is there globally, but it is true for the Indian Ocean as well. But in Indian Ocean also has some more specific thing. So before 2010, so this is a picture from Levitas et al. 2012, where the trend of the heat content is plotted here for upper 2000 meter. So this is for the global ocean. This is latitude. What you see here in the tropics, if we talk about only tropic, it is -30 to +30. You see both the hemispheres got the fair share of heat. So it's kind of symmetric in the globally. In the Pacific, northern hemisphere got a bit more than the south, whereas in the Atlantic, it is pretty much symmetric. But when it comes to the Indian Ocean, if you look at the tropic, the northern hemisphere, the North Indian Ocean got more heat. And in fact, the South Indian Ocean lost some heat during this period, up to 2010. But something happened in the last few decades that the South Indian Ocean started to warm much faster than the North Indian Ocean. So I'll be discussing more that, okay, what are the processes that actually drive this? There are a few papers that came in the last decade. They talked about this rapid warming of the South Indian Ocean, and they linked that to the ITF. So what happened is that after 2000, Pacific went into the La Nina kind of a phase, or negative phase of the PDO, and that led to strong ITF, or the ITF enhanced. So the Western Pacific is very warm. So when ITF is enhanced, this warm water pushes into the Indian Ocean, and then that caused the South Tropical Indian Ocean warming. So that is the basic understanding till today we have. And this is a picture which is depicting that. So this is a period from 1993 to 2002, and this is the longitude. So this is the Indian Ocean, this is the Pacific, and this is the Atlantic. What you see here is that the Western Pacific is very warm in the subsurface. This is depth, whereas the Indian Ocean lost heat during that period. But in the next decade, 2003 to 12, the subsurface of the Indian Ocean started to warm. And the theory that I just said, that the ITF become very strong or strengthened during that period due to the negative phase of the PDO, and that led to the pushing of the extra heat into the Indian Ocean. That is what we talk about, the global climate hiatus and so on. But there is a twist after 2010. So let's look at this black curve here. So this black curve is representing ITF. So this is the ITF scale. So around 85, it was about 18 Swavrut. So it's a negative, means it is towards the Indian Oceans because it is the westward flow. And then it decreased up to 1995. So from minus 18.5 to about 17. So it decreased, the ITF decreased from 80 to about 95. And then after 95, there is a sharp increase in ITF, say up to 2010. And this decadal variability of ITF is kind of linked to the PDO, which is the blue curve here. The PDO scale is here. So when PDOs become too negative during this period, ITF responded and then ITF becomes stronger. And that's what led to the South Tropical Indian Ocean warming during that period. But PDO is a oscillation, right? So it actually reversed, started to reverse from 2010, that is the blue curve here again, and ITF responded. So ITF started weakening very rapidly after 2010. But the story lies here, which is my interest, that is the red curve, that is the D20 of the South Tropical Indian Ocean. So what happened when the ITF is very strong, they pushes extra warm water to the South Tropical Indian Ocean, D20 goes down in the South Tropical Indian Ocean, that is the 20 to 30 south domain. And then that is the Indonesian through flow. Oh, sorry, So Indonesian through flow has strengthened. So it pushed the water to the South Indian Ocean, and that led to the upper water column warm, and the D20 become deeper. So this D20 become deeper here. So negative means it is going deep. But the ITF reversed after 2010. So until 2010, the D20, that is the red curve, is kind of following the ITF. So when it is decreasing, D20 shallowed. When ITF strengthened, D20 deepened. But after 2010, ITF reversed, but D20 not. D20 continued to deepen. So there, the correlation between the D20 and the ITF somehow got disconnected. So there is something more have started happening after 2010. That is 20 degrees Celsius, 20 degrees Celsius isotherm, the depth of the 20 degrees Celsius isotherm. So basically, the depth of the thermocline. So when the more warm water is there, then thermocline going down. So the D20, that means the thermocline depth is become deeper. But the thermocline is continue to deepen, whereas the ITF actually weakened. Okay, so this my point of interest is somewhere here. So that why that decorrelation happened. So earlier Pacific was well connected with the Indian Ocean through the ITF, that is Indonesian through flow. But after 2010, something happened that the correlation did not working out well. So we found that the reason lies with the Southern Ocean. So not only the South Indian Ocean is connected to the Pacific through ITF, but this region is also well connected to the South Indian Ocean. So this is a schematic showing the subtropical gyres of the South Indian Ocean, Pacific, which is got cut, and then the Atlantic Ocean. And these subtropical gyres are connected by this ACC, Antarctic Circumpolar Current, driven by the westerlies. So this entire thing is called a super gyre. So water flows west to east and then return back through these gyres, and they connect all three basins. They are called super gyre. Okay, there are three sub gyres for each basin, but they are also connected individually and called it as super gyre. What happened is that in the recent decade, this because of anthropogenic warming, Southern Ocean become very warm. So subpolar low become much lower, subtropical high become much higher. So gradient become very strong. So the westerlies are now very strong. So you must have seen that the Southern Ocean westerlies are becoming very strong in the recent decades because of this anthropogenic warming. And this westerlies, as it is becoming stronger, it is also going towards the pole. That is called the Southern Ocean, Southern Annular Mode, which is becoming positive. So the westerlies are going towards the pole, and westerlies are going towards the pole. This subtropical gyre will come with it. So they will also pull towards the pole. So this is a basic story behind it. And there is a relation between the subtropical gyres, which are driven by this high pressure system there, that is sea level pressure. So this black is sea level pressure. So, and this red one is the SAM, that is the southern annular mode. So the southern annular mode is positive. That means the westerlies are becoming stronger and stronger, moving towards the pole, starting from 1955 and so on. They continue to become positive because of the global warming, and this sea level pressure is also strengthening sea level pressure in the Mascarene high region. That means in the where the subtropical gyre is, and they are very well correlated in terms of variability. So the correlation is more than 0.5 if you take that entire record, which is about 1962 about 2020, and the correlation in fact strengthened between 1980 to 2000. But after 2000, this correlation gone down. So the correlation between the South Tropical Indian Ocean and Southern Ocean actually lost. And in fact, they show a negative correlations. And if you look at the trend also, the SLP is having a negative trend, whereas the SAM is continue to have that positive trend. So that the correlation between the Southern Ocean and the South Tropical Indian Ocean is no longer working. Why it is? Because that as ITF is pushed a lot of warm water to the South Tropical Indian Ocean, Southern Indian Ocean become very warm, and once you have a warm water, then it actually decreases the sea level pressure there, because you actually infuse a upward motion in the air, so that sinking will decrease. So there, that the high pressure system that SLP was increasing as SAM was increasing doesn't work out after 2000, because you have pushed a lot of warm water in the Indian Ocean, and then SLP is actually going down instead of going up, synchronized with the SAM. This can be seen here. So this is basically the showing that okay, how subtropical gyres are connected each other, and their entire subtropical gyres are strengthening, and but they are also going to the pole. So this is the latitude of zero wind stress curl. So your wind stress curl changes where the westerly and the subtropics, and this is the zero wind stress curl latitude. So that means the southern part of the subtropical gyres. So this is the latitude of southern boundary of the subtropical gyre. So what you see globally, it is going south. That means the all subtropical gyres together, they are going towards the pole. In Pacific, it is very prominent. But in Indian Ocean, it was going south up to 2000. But since ITF pushed a lot of warm water, SLP and the Mascarene High and the Southern Ocean link got broken. So the Mascarene High is not going south anymore. So the relation, because of the extra heat that came into due to the global climate hiatus, they caused a problem in the South Indian Ocean and broken the link between the South Indian Ocean and the Southern Ocean. And as a result, two gyres are going south, Pacific and Atlantic, but Indian Ocean is staying at the same place, causing an extra gradient south of Australia, and that leading to the Tasman flow enhancement. So this is the Tasman flow, which is south of Australia, Pacific to the Indian Ocean. It was increasing negative because it is towards the India, so towards the Indian Ocean, westward flow. And you see this is the trend. So Swabrook transport has increased, in the last decade, because that Pacific is going down, subtropical gyre is going down, but the Indian Ocean not. So there is an extra pressure gradient between Pacific and Indian Ocean, south of Australia, that enhances the Tasman flow. ITF is weakened mildly over that entire record, but Agulhas is also weakened. So Agulhas was strengthening before, so the water from the Indian Ocean was going more to the Atlantic Ocean, but in the recent decade it has weakened. Why? Because subtropical gyre is actually weakening in the Indian Ocean because of Mascarene High is weakening, and the subtropical gyre of Indian Ocean feed into the Agulhas current. So since the subtropical gyre is weakening, it is feeding less, so the Agulhas is also weakening. So, and one side Tasman is coming, strengthening more, but on the other side Agulhas is weakening. So that means there is a convergence that is happening in the South Indian Ocean, and this convergence leading to the warming of the South Indian Ocean further, even though ITF is not contributing anymore. So this is presented in terms of a schematic here. So here you are supposed to have a high pressure, but this is an anomaly. So now in the recent decade, you are getting a low pressure anomaly. That leading to the subtropical gyre weakening, not feeding well Agulhas current, so the Agulhas is weakening. At the same time, this Pacific subtropical gyre going south, but Indian Ocean is not, so Tasman leakage has increased. So the extra water coming into the Indian Ocean, and this is a feedback loop that actually constitutes. So South Indian Ocean warming first due to the ITF, weaken Mascarene high, and that lead to decorrelation between Mascarene high and the South Indian Ocean, SAM. So the poleward movement stalled and then increase the Tasman leakage. Once you increase the Tasman leakage, that convergence happened. Another thing is that weaker trade winds reduce Agulhas, and that also leads to convergence of heat, further warming of South Indian Ocean. So this is a positive feedback loop that continue to warm South Indian Ocean, deepening the thermocline further, even though the ITF is not responding well. So this positive, because of this positive loop, we are actually seeing a stronger decorrelation between Indian Ocean and the Southern Ocean and the Pacific. So that's all, and I hope that this feedback loop will break because of natural variability of something, and then we'll go back to our natural cycle of ITF Indian Ocean connections, and that's all. Thank you. So this paper we actually submitted for a review. It's an under review, but the preprint is available for a reading. If you are interested, please. Yeah, I'll take up any questions if you have.
Any questions for our speaker?
Are you conserving mass, or are you putting extra mass into the Indian Ocean?
The converging mass. The mass is conserved, but the mass is converging to the Indian Ocean. And not only the mass, that extra heat also that is associated with that.
Consistent with sea level?
Yeah, so in fact that is leading to the stearic height induced sea level rise. And that is being kind of shown by many others. That,
bottom pressure?
Yeah, I am not.
If you're adding mass, it has to show.
Yeah, that should reflect in the bottom, but we have not looked at it.
Thank you, Abhisek, and that's a nice talk. So, but this particular phenomena is a signature of any human-induced change, or it is a part of a variability?
It is basically a feedback between the different basins, how they connect. So there is a natural feature that, okay, ITF connect to the South Indian Ocean and the South Indian Ocean connect to the Southern Ocean. So they all together actually constitute the variability that we observe. But what happens is there is something different happened due to anthropogenic warming in the South Indian Ocean. And at the same time you had the negative phase of PDO. So because the negative phase of the PDO is so strong that it pushed a lot of warm water to the Indian Ocean, and then there is, because of this extra heat, you are having no connection, you are actually losing that connection between the Indian Ocean and the Southern Ocean. Not losing the connection become altered. Okay, and because of these altered connections, you are actually seeing the ramifications, how it implicate further. So there is a perturbation that is given by the anthropogenic warming, and that leading to a different set of variabilities now. So I'm not talking that, okay, some trend has changed, because we do not know. As I said that, okay, it is always part of natural variability. So I'm sure that there is something, again, something will happen and then it will come back to this normal state. Yeah, so that's all. So it will come back to something.
Yeah, thank you.
Yeah, I'm not sure that what will constitute to reverse this warming. Yeah.
Time for one more quick one.
Okay, no, sorry, I just had the same question about the mass. I mean, do you mean the mass of the upper layer, or so the upper, above the thermocline is increasing, and that's what's giving this warming signal? Or, you can't increase the mass of the whole layer unless you're adding more water, right? And you're not adding that much, right? I mean that.
Yes, so it is not that the huge amount of extra mass. It is about 3 sub root if you see the net gain over the last decade. but it is enough to have to get you a stronger signature in heat content in the upper layer, because the most of the flow is actually
So it's the
happening in the
mass of
upper
the
layers.
upper layer that you're...
Yeah,
you're-
most of the exchanges I'm talking about is in the upper few hundred layers, about 500 or so.
Okay.
Okay, let's
So it is
think.
basically redistribution among the other basins to the Indian Ocean.
Cool. Well, let's thank our speaker again.
Thank you.